Anem a la nostra ponència. Mireu, us explico. La natura és una font d'inspiració inesgotable. Segur que quan parlem d'això us ve al cap Antoni Gaudí, l'arquitecte de la Sagrada Família, que es va inspirar amb la natura, amb les copes dels arbres, per dissenyar el gran temple de la Sagrada Família, i li va funcionar. Home, li va funcionar. Per què? Doncs perquè imitar un model que fa milions d'anys que funciona, que la natura ha desenvolupat i que sabem que va, doncs evidentment sempre és una garantia d'èxit. D'això se'n diu bioinspiració, del que va fer Antoni Gaudí. I els informàtics, igual que Gaudí, també la utilitzen. Us preguntareu com ho fan i per què ho fan. Explica'ns-ho. Doncs, per exemple, per a resoldre una de les principals necessitats de gestió i conservació de les dades, com és l'emmagatzematge. I com ho fan? Doncs bé, el volum de les dades, ja ho sabeu, creix exponencialment. Això és com la roba del meu armari. No sé com és i cada dia n'hi ha més. Doncs les dades igual. I l'emmagatzematge consumeix uns enormes recursos energètics que són insostenibles des del punt de vista mediambiental. Ja les granges de servidors no paren de créixer i això és un consum d'energia molt gran, procedent en bona part actualment encara de recursos fòssils. Doncs bé, a la següent ponència, que s'emmarca en el principal sistema, o sigui, s'emmarca dins del principi d'aquests sistemes bioinspirats. En aquest cas particular, el que fan és, atenció, que parlem d'emmagatzematge, és utilitzar molècules d'ADN com a sistema d'emmagatzematge de la informació d'una manera que no consumeix pràcticament energia i la seva capacitat, atenció, és infinita. A mi hi tinc moltes ganes que ens ho expliquin. Aquest és un dels projectes disruptius, jo diria que més importants avui dia en aquesta matèria i per això en aquest congrés, que sabeu que som supertop, no ens ho podíem perdre. Arriba el que hem anomenat la revolució de l'ADN, aquest congrés d'arxivística, de la mà de Pierre Crozet, de la Universitat de la Sorbonne. Ell és professor associat des de l'any 2017 del Laboratori de Sistemes i Biologia Sintètica d'Algues i especialització agroalimentària de la Politècnica de la Sorbonne de París amb Biologia Computationnelle i Computativa. L'escoltem ara mateix, un fort aplaudiment per Pierre Crozet. Endavant.
Good morning, everyone. I would like first to thank the organizers for inviting me to this very, very fine seminar. So indeed, thank you for the introduction. So I'm Pierre Crozet. I'm associate professor at Sorbonne Université, and I'm also co-founder and chief technical officer of Biomemory. So as a starting point, I need to tell you maybe something you all know, but I think it's important to say it again anyway. So current digital media are highly limited, and while our storage needs are exploding and will explode even more. So just this is the amount of total data in the world, what we call the data sphere, so the digital data. And be careful in the axis, this is in zettabytes. So zettabytes are 10 to the 21 bytes. This is absolutely enormous. So if you want to have an idea of what this means, it means that if you want to download 1 zettabyte at 100 megabytes per second, which is like optic fiber connection you have at home, it will take you 2.5 million years. So this is absolutely enormous, and this amount of data is actually increasing exponentially. And the major problem with this increase, as Dr. Karin Strauss was saying from Microsoft Research, is that some years ago she was saying that we could store today, so 30% of the information we generate and we want to store, but by 2030 we'll be able to store about 3%. So I guess there's a lot of work for archivists in the future. And this is another way to say the same thing, is that this blue area is basically the amount of data we will need to store, will want to store, but will not be able to store, or a zone of potential insufficiency. And this is due, and this data can be classified in 3 different types. I think you probably know that better than me. In hot data, warm data, and cold data, and archives are considered as cold data. And just this graph to show you that the price of the data storage is directly proportional to its warmth, meaning the probability of accessibility of the data. And this is the way the data lives. So it starts warm in certain types of medium in terms of storage, and then fast it goes to hot, then it goes to warm, and it ends up as an archive or cold data. And the probability of accessibility of this data is extremely low. I wanted to introduce you another term, which is WARM, for write once, read never. This can be the case of archives. Most of the time archives can be valorized, but in computer sciences, in digital data, most of the data are WARM data. And in function of some different estimations, we consider that more than 60%, it can go up to 90% of the world data, digital data, are archives. And so most of these data will never be read, but will never be deleted. And most of them are stored on magnetic tapes. So for the ones of you that don't know what magnetic tapes are, for the less young of us, you might remember the VHS that we used to put on the TV to watch our favorite movies. These are magnetic tapes. It's the same thing, but more performance. And they are stored in that kind of machines, and they are stored offline. Most of the data storage, current digital media storage devices present three main issues. The first one, which is here, is that they are extremely fragile. Indeed, in data centers, most of the supports have to be changed every 3 to 7 years. 3 years for hard disk drive, 7 years for magnetic tapes. So this is a real economical and environmental issue. The second problem is that they are bulky. So nowadays, if we estimate that the whole surface occupied by data centers in the world is more or less twice the size of Paris, which is more or less 1/1,000,000th of the land on Earth. But with this exponential increase of data we are living, basically we are going to reach by 2040 1,000th of the land surface. So this is absolutely important and incredibly high. And final point, but not the least, is that data centers are extremely energy consuming for computing, so using the actual machines, but also and mainly for storing these digital devices, because they request to be stored at a specific temperature and a specific hygrometry, and that costs a lot of energy. Just to give you an idea, the estimations, this is the lowest estimation, all data centers in the world are consuming already more than 2% of the electricity generated in the world. Some people say up to 4%. In some countries like Ireland, at one point the government had to say stop, because the data centers were consuming up to 20% of the total electricity in the country. And of course, quite important point, the carbon footprint of this industry, because it's an industry, is already higher than civil aviation. So you can always wonder, am I going to keep my emails or take the plane? That's almost the same question nowadays. So all of these problems clearly have an impact on the environment, and I think we can easily say today that this is a point that it should be taken very seriously. So we need a revolution to store data nowadays, because we would not have enough devices to store the data we want to store, and the way we store them is not ecological, so we need to shift. Many people start to look at how nature is doing. Nature is storing information, and nature is storing information into a particular molecule that you've all seen one day, at least in a movie or a commercial, which is this molecule. It's DNA. So DNA is the data storage device created and selected by nature over 4 billion years. As you are archivists, most of you, just a brief reminder of what is DNA. Is this molecule, you can see that actually there are 2 strains, this famous double helix that you have seen somewhere already. So this is one molecule, this is another molecule, okay? It's 2 strands. This is the chemical structure. I'm not going to enter into the detail, but what is important is that the alphabet that is used in DNA is 4 letters, A, C, T, and G. And this is a molecule that is extremely dense. Just to give you an idea, in each cell composing our bodies, there is the DNA that is called the human genome, that is basically all the blueprints to build your organism and how to make it function. And this human genome corresponds to more or less 3.2 billion pairs of these letters. If I do a calculation, basically it's more or less 1.5 gigabytes per cell. If I multiply this amount by the amount of cells we have in our body, the average amount, then globally, each living human being contains more or less 5 zettabytes of data that is used for its biological purpose. So why turning into DNA instead of the fact that, okay, it's used by life to store information? Basically, DNA has the exact qualities that the other media have defects. So it's extremely stable. You can keep it over millennia. Just as an example, we're able to read the sequence of an old fossil of 1.6 million years old. So I can say it's really stable compared to any type of data storage, including paper. It's extremely dense, so I had already explained you on our body, but if we use it to store information, if we want to store all the 100 zettabytes that I introduced you just before, it will take you more or less 200 grams of DNA. So basically, a small chocolate bar, the size of a small chocolate bar. And most importantly, DNA was conceived by life to need no power upkeep. You don't need to put energy to keep it stable over time. So at room temperature, anywhere on the planet, you can keep it stable for a very long time without energy input. All of this making it really, a priori, the best solution to answer the problem that we have with all the other data storage devices. How can we do that? So I'm going to explain you this graph one step after the other. So I think all of you perfectly know that all files encoded are encoded in binary sequences of bits, 0 and 1s. And the first thing we need to do is to shift from one alphabet to the next, or we have to code the data. So we have to shift from binary to quaternary alphabet. There are lots of different ways to do it, and a lot of computer scientists are working on that. So I'm just going to show you 2 simple examples of how to do it. The first way is to choose no redundancy, maximum density possible, 2 bits per base. Base are these letters, I remind you, bits are 0 and 1s. So each time I want to encode digital data onto DNA, and I will find 2 zeros, I will put an A. 0, 1, I will put a C, 1, 0, a T, 1, 1, a G. Relatively straightforward. But there's another way that can be used, which is the one we use, and I'll show you later how, which is 1 bit per base. Because DNA is a biological molecule, it's a molecule, is not an electricity signal like the 0 and 1s in the computer. So it might be very interesting to have redundancy in the way we encode. So each time we find a 0, we can put an A or a C. Each time we find a 1, we can put a T or a G. So this is the way we code the data. We pass from binary sequences into DNA sequences. Until now, I was in the virtual world. Now I need to pass into physical, real world, meaning I need to write the DNA sequence. I'm not going to enter into the details of the chemical reaction and show you that, just to see that it is a bit like the Legos we saw a bit before. So we have the different bases that A, G, C, and T that we can assemble one after the other to have the exact sequence that we want that will encode the data that we want. And so by different reactions, we can add specifically only one of these 4 different bases. And by repeating the cycle, using this heavy chemistry, we can obtain at the end the exact sequence wanted. Here we are going to have a single-stranded DNA. So not the double helix I showed you before, just one strand. It's functioning extremely well, this chemical synthesis. The only problem is that the building bricks are called phosphoramidites and are coming from a really heavy chemistry. They are unnatural DNA components that are needed to control these reactions to end up with a real DNA molecule. And the price, I will come back to that later, is relatively expensive still. So, as I just told you, we are generating oligonucleotides. That's what we know how to create, how to write the data. And so, The first people that started this field in 2012 was the George Church group in Harvard. In 2012, decided to encode several files for more or less 650 kilobytes, which corresponds to roughly 55,000 oligonucleotides, so these small DNA single-stranded molecules, which are represented here. So how can we do that? So we are just going to encode the data the way I just explained you, here in this purple section for more or less 96 bases. And then, as you understood, we have a lot of oligonucleotides. So if I want to read the data and to reorganize it, obviously I will need an index. I think you understand that better than me. So you keep a portion of this molecule as an index. And then, because I told you this synthesis is expensive, then we need a way to amplify it easily. And this is technical details in biology, but you had some sequences here that are the same for all the different oligonucleotides that encode different information here that will allow us to amplify it, thus to read it easier, more easily. So this was the first demonstration, but globally we reached this huge demonstration, which was never, we never went above such a demonstration because of the complexity and of the price of such demonstration. In 2018, Microsoft Research, University of Washington, and Twist Bioscience encoded 200 megabytes of data on 13.4 million oligonucleotides on more or less the same structure. So this is the way most of the people are writing. Then you have the molecule. So you need to store it. So there's different ways to store it, but the best way to store will be if you know how you protect the DNA from what might damage it. So DNA is sensitive to three different things: water, light, and oxygen. And so basically you can store it in different fashion, but at the end what you want to do is to store it dehydrated, so you remove the water from the molecule, in an opaque recipient to avoid light to enter, and sealed away from air. And so there's different ways, including specific type of papers, the FTA papers that are more or less 20 years stability of the DNA molecule. Then you can have DNA, silica nanoparticles, in which you can reach easily 100 years of DNA stability. And then you have a solution created by a French company called Imagen, which are these small capsules in which they guarantee 50,000 years of stability for the DNA. So I think we have all the possibilities and we can store really almost forever the DNA without any problem. So that is for the storing part. Now I'm still in the physical world, but at one point I need to access the data. So to go back from physical world to the virtual world. This we know how to do it for quite a while. This slide is just to show you Frederick Sanger that invented in 1990 the sequencing of DNA molecules. And since then, several generations of different machines that I'm not going to detail allowed us to have really huge input of the sequencing. And just as an example, today we are using that type of sequencing machines. So this was half my size, and this is the size of a USB pen of that size that you can take everywhere. So this is a sequencing machine that was used, for instance, to sequence the variants of the COVID. And one important point is that thanks to these technologies I just showed you, the price of sequencing, for instance, a human genome, if we use it as kind of a reference, which originally the first time we did it took 10 years, and it cost $2 billion to do it. That was not even here, it's even before. Nowadays, the price for sequencing one human genome is between $100 and $200. And we think it's going to reach $10 in near future. Just as an information, the human genome is between 15 and 20 gigabytes of data. So you see the reading of the data is not really a challenge in this scheme. And then once we have the sequence, once again on our computer, then we decode, and then we have our file. And I think from what I just showed you, you already saw that the bottleneck is here, is the writing. And that's where we come into play. We think in our lab and in the company, in Biomemory, that there are limits that I showed you of DNA storage on oligonucleotides. It's great, but there are some limits. And so our vision is to exploit the potential of nature of living cells to answer these problems. So really use biology to remove the limitations of DNA data storage. Why? Because biology invented DNA. And thus, biology knows how to manipulate DNA very easily. Almost all the different types of actions we need to do. For instance, DNA copy, DNA reading, editing, error correction, random access, or signal amplification, these different things. Living cells do that extremely well. And so the idea is to use a new approach in biology that we call synthetic biology to domesticate the DNA and the cells to make a new technology of DNA data storage. But to do that, as I told you, we're using oligonucleotides, these small single-stranded DNA molecules. You cannot use that with living cells. Living cells are using double-stranded, that's why you all know this double helix figure, and long fragment, not short molecules of 200 bases. If you give that to a bacteria, it will destroy it, and you will lose your information. No, it needs very long molecules like chromosomes. And so our strategy to be able to harness the power of living cells to do this technology, this manipulation, is to create biocompatible DNA that will be able to be manipulated by the cells for us easily. If we say that, the first thing that we have to keep in mind is that we need to have a biosafe DNA. So if I encode your last vacation family picture, you don't want to encode a toxin into it. And so what we did, once more, it's biology, I'm not going to enter into the detail, but this is how it works. DNA is here and is encoding information for a cell, for a living cell. And so what we want to do is to forbid this information to be generated from the DNA that is encoding digital information. The best way to understand that is that if you don't speak Chinese, I give you a text in Chinese, you will be able to copy it, but you won't understand it. That's exactly what we have done. So it's impossible for the DNA that encodes digital data that we created to encode biological information. And so once we created an algorithm that allows to do that, to generate biocompatible and biosafe DNA, then we had to generate a format that will allow to organize the data onto the DNA. And that's all of this is what we call the DNA drive, which is what we call the next generation of cold storage media. It has many interests. What I already told you is biosafe, but also it's of unlimited capacity, and you can copy it at very low cost. And keep in mind that copy in computer science is the first operation you do. You always copy data for not losing them or for moving them. The way we wanted to organize the data, and for once we didn't look into biology, we looked into computer science, is how an hard disk drive is functioning. Without entering into the details, inside an hard disk drive, you have this structure with platters, then with tracks, and with sectors like this. And so our molecule are big DNA molecules that are circular. So we organize them the same way. This is the unit. This is a molecule of DNA that you see is circular. And inside, you have sectors that contain the data, then indexes to be able to reorganize the data easily and also go to do random access easily also. These molecules are then going to be pulled and put into an array that then we call the DNA drive. This is the complex figure that I'm not going to detail. It's just for you to know that if you're interested, we have an article that is freely available on the bioRxiv repository server. So globally, today, what other people are doing, the mainstream strategy is to have oligonucleotides that are pulled like this, and you can see them as small pieces of paper, and then you have to put them all together to reconstitute the book. The way we do is to use pages that have this text, the tracks, that are divided into sectors. Then we have the pools, that could be like a book, and then we have an array that could be a bookshelf, and the DNA drive would be like a library. So that's the way we consider the DNA drive. We are academics, my colleague Stéphane Lemaire and myself, and we patented this technology, and we decided that it would be interesting to have a startup that is going to push it forward to the market. And so we created a company called Biomemory, which is a spin-off of Sorbonne Université and the CNRS, together with Irfan Arwani, which is a computer scientist and serial entrepreneur. And just to show you what we've done to show that the DNA drive is actually working, so a proof of concept, we did this project which is called la révolution de l'ADN in strong partnership with the Archives nationales, French National Archives. So we chose two very important historical texts for French people on an original idea of the student association Alma Mater, the Declaration of the Right of Man and the Declaration of the Right of the Women. And we did that, of course, in collaboration with historians, with archivists, with philosophers, and with computer scientists. So we did the encoding, basically what I explained you until now, and we obtained these different molecules. So there's more molecules for the Declaration of the Right of the Woman because the text is longer for historical reasons, and one for the Declaration of the Right of Man of 1789. And we store these DNA molecules into small capsules, so the ones I showed you earlier. If you want to see them real, you can come to see me after. This is the size. And inside these capsules, as copy is almost for free using our system, we stored 100 billion copy of the text, each of them. So I have the other capsule here for the women's rights. So in here, we have more than 100 billion copies of the text. Of course, we reopened some of the capsules because we did more than 250 capsules like this, and be sure that we could read fully the information inside. So we consider that we preserve for thousands of years with no energy input these two foundational texts. This is what we've done. So we started not from the image, we started from the text. Of both, we obtained a binary file, we did digital compression like zip or RAR kind of compression. Then our algorithm, we got the biocompatible DNA, which is biosafe. Then we asked Twist Bioscience to synthesize the small fragments, and then they send us. Then we assembled these fragments into our molecules, this famous track that I mentioned several times. We amplified using bacteria only in a lab. No bacteria exited the lab. And we extracted the DNA, so bacteria just selected and amplified a lot of time this DNA for us. And then we stored it. For some of them, of course, we read using the small sequencing machine I showed you earlier. We obtained the DNA, we decode and obtain the text again. To go further, as this text has a really important significance for French people, we decided to work from the start of this project in collaboration with the French National Archives, and this is Bruno Ricard, the current director of the National Archives, and we decided to deposit officially one of each capsule, so one for each declaration, in the National Archives, in this vault that was created at the French Revolution to store the Declaration of the Right of Man. And so we stored officially the 23rd of November 2021 in this vault, which is called l'Armoire de Fer. These two capsules, which are stored here officially, making the French National Archives the first public institution storing data onto DNA officially. And so this is the DNA drive. As you understood, we can do copies at very low cost. But let's be honest, this is still extremely expensive to do. So it's more than $1 per megabyte, which is more or less the price that were the SSD drive 10 years before they were commercial, more or less. And the reason comes from that, this chemical synthesis. On top of it, this chemical synthesis is using not natural molecules, so it's using hazardous flammable organic solvents to do these reactions. There's another strategy existing, which is called enzymatic synthesis, but even if it replaces the organic solvents that can be polluting, they generate the same type of molecules, and the raw material they are using, the building bricks to build the DNA molecule, comes from petroleum chemistry for now. And so we reason differently. We turn once more to biology to see how can we solve this problem. So if you want to generate any type of DNA molecule, for instance, for 8 nucleotides, you need this amount of different possibilities. You need to be able to synthesize that. And that's what these two technologies are doing perfectly well. But if you want to encode digital data, then you have a limited complexity because you encode bits using this 0, 1 into the AC and TG. And so what we did was then you need to encode 256 sequences, which is much simpler to manage. And so our solution is basically to do like printing something. We will have 256 different inks that have a bio block that encodes digital data, predetermined, and then we can just replicate them because, of course, these sequences are biocompatible and biosafe. They fit the DNA drive algorithm. And then, I'm not going to enter into the details in here, of course, we have these two libraries and we can assemble the data into the final level, the track, using these two banks of bricks that contain very small amounts of digital data encoded into DNA. And why we think it's going to change everything is because, as you see here, the building bricks that ends up being the thing that cost the most in these two different ways of synthesizing DNA, we replace it by something that is created, not created, but replicated by bacteria that just need sugar to produce them. So we turn sugar into a hard disk drive. This technology is 100% biosourced, so it's renewable and it's biosafe. To finish, we continued our partnership with Archives Nationales. We are still encoding 3 new texts, so the decree abolishing slavery, the ordinance that granted women the right to vote in 1944 in France, very late, and the Badinter law in 1981 that abolished the death penalty. And we are doing that currently using our technology I just described you. Our vision, and this is my last slide, is to enter the data centers in 2030 using really what computer scientists are using, meaning a rackable DNA, rackable server. So we want to create this rackable DNA data storage server. I thank you for your attention and can take any question if we have the time.
Fantàstic, Pierre Crozet. Fantàstic. Estic al·lucinada. Com esteu vosaltres? No he entès la meitat de coses, perquè sóc de lletres, però he entès moltes coses molt interessants que, si li poso el translator que m'entendrà, perquè si ho haig d'explicar tot això en anglès no podré, o sigui, seria incapaç de fer-ho. La dadesfera no l'havia vista mai, no l'havia visualitzat i he quedat esparverada. És a dir, jo que ja he hagut de contractar 2 terabytes de memòria a l'iCloud perquè ja no hi quebo en el meu iPhone, doncs imagineu-vos, això li deu passar a tothom, a tots nivells, a nivell mundial. Aquesta dadesfera que ens ha dit que es calcula amb zettabytes, i diu, perquè us en feu el càrrec, un zettabyte per descarregar-lo necessiteu 2,5 milions d'anys, jo crec que ho he entès bé, ho heu entès igual que jo, no? I llavors he mirat aquell índex que ja portem 170, o portarem uns 170 zettabytes el 2025. Dic, mare meva. Però el més gros de tot que m'ha fascinat del que ha dit és que el 90% d'aquests arxius que guardem són porqueria pràcticament. Són aquests Word, no? Que els llegim una vegada i no els fem servir més, però els guardem. Això ens passa a casa igual, us passa, no? Guardem coses, escolta'm, no pot ser. Ens passa això. La solució quina és, ens deia? Home, doncs la solució és l'ADN, perquè sabem que ja funciona en el cos humà. Escolta'm, això ens ha de funcionar perquè nosaltres tenim entès 5 zettabytes a dintre del nostre cos durant anys i així anem funcionant, que si els transformem és una rajola de xocolata, dius, home, això és com més portable, no? I ens deia, clar, què ens cal fer? Cal passar del famós sistema binari al sistema quaternari. Això ho he entès bé. Com fer-ho ja m'he perdut una mica. Suposo que vosaltres també, però jo ho deixem als superprofessionals del tema. Llavors ens ha dit com guardar-ho, com ho guardem. He pensat en els gremlins, perquè ens ha dit els 3 grans enemics de l'ADN. Un és l'aigua, què passava als gremlins si els mulles després de la mitjanit? Es reprodueixen. L'altre... Costa fer això que faig, no penseu, L'altre és la llum, he pensat en el Dràcula, no? Vale. Ara ajudeu-me vosaltres. L'altre gran enemic és l'oxigen. He pensat, no sé, amb els extraterrestres, no sé, he pensat la dimensió desconeguda. Aquests són els 3 grans enemics. Com se soluciona això? Tancant-ho amb un cilindre en tesca de silici que ja ha fabricat una empresa francesa i que, escolta'm, el que hi ha allà dintre, que són els que porta ella a la butxaca, duren 50.000 anys de moment. Diu, pràcticament això és infinit. Això seria... No, més. 1,000. Més. 50.000 milions d'anys. Sí, va, ho he entès bé. I diu, això...
1,000.
100.
Not million.
50.000, no? 50.000 anys.
1,000, yes.
1,000, ho he entès bé. Vale. Després, d'això se'n diu un drive d'ADN. El drive ja sabem el que és, no? Ens l'ha ensenyat. Aquí tenim un drive d'ADN, que és la manera segura de guardar tot això. El problema quin és? Jo ja l'he entès també, a part de tot el que ens ha explicat després. Els diners. Els diners. Això ha de ser molt barat, però fins que arribem aquí, de moment, val molts diners. Ens deia, el cost de moment és $1 per megabyte. Això és molt, però com tots els altres exemples que ens ha posat de coses que abans eren molt cares i ara, amb el temps, no ho són tant, esperem que aquesta tecnologia es desenvolupi en aquesta spin-off que ha creat el nostre convidat Pierre Crozet, que es diu Biomemory. Un aplaudiment per ell, confiem que això tiri endavant. Moltes gràcies. I ara sí, escolteu-me, la Margarita ja en fa. Anem a dinar. Us diré coses tornant, perquè ara suposo que teniu gana. Anem a dinar, dinem al mateix lloc on esmorzem.